Okay, so I'll first apologize for the audio of the second homework assignment, and I've made some adjustments, so I hope this is a lot better. So here is assignment number 3, and we begin with the chapter 5 questions, and the chapter 5 questions begin with question number 1. And question number 1 is describe in words how to compute. Okay, see this P? Just call it probability. So in words, how do you compute the probability of X? Well, the probability of X equals the times that X can happen divided by the total number of outcomes. For example, the probability of a heads is the times that a head can happen out of the total outcomes, which are heads or tails. So the probability is 0.5. So that is the answer to question number 1. Question number 9 is state the formula for calculating each of the following. Okay, so this can look or sound a little tricky. It really is not. Okay. The mean of a probability distribution is every possible thing that can happen multiplied by its chance of happening. So the chance of something here happening is lower than the chance of something here happening. So how would you calculate that? That would be the sum, and this is the sigma, the Greek letter sigma. So sigma sum, you Greeks out there can go crazy with that. So it's the sum of every X times the probability of that X. So that's the answer to A. So B is the variance of a probability distribution. The variance of a probability distribution would be every X here minus the mean, so every X minus the mean, and you see some of these would result in a plus number, some of these would result in a minus number. So how do you get rid of that plus and minus? You would square it, and every one of these would have to be weighted by its probability of happening. So this would be like that, and that would be the variance. The variance is sigma squared. So what does that mean here? That means if this is a variance, remember, the variance is something that you get by squaring these numbers. So how do you back that out to get the standard deviation? Well, you would take that sigma squared and just take the square root of it. That's supposed to be a sigma. It looks like a gamete, right? I'm not a science person, but I think I remember that from my high school science days. So take the square root of that, and that is the standard deviation, which is a sigma. So that is question number 9. That takes us to 11. Turn the page here. And question number 11 is, a hypothetical population consists of 8 individuals. So let me create some space here. So we have 8 individuals. We have a 13-year-old, 14-year-old, 17-year-old, 20-year-old, and 21-year-old, 22-year-old, and a 24-year-old, and a 30-year-old. Okay, so suppose you were selecting these people at random. That is, you just close your eyes and you spun around and then saw who you would be pointing at. Okay, so the question is this: what's the probability that a person in this population is a teenager? Well, how many teenagers do you have? You have this teenager, you have this teenager, you have this teenager. That's it. So 3 out of how many? 1, 2, 3, 4, 5, 6, 7, 8. 3 out of 8 are teenagers. And from my stock trading days, I remember that that is 0.375. So the likelihood is 0.375, or the probability of getting a teenager is 0.375. So the next question is, what is the probability of selecting a participant who is at least 20 years old? So this person is 20 plus, 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 this person is 20 plus. So we have 1, 2, 3, 4, 5 of the 8 are 20 plus, and that equals 0.625. So that makes sense, right? 0.375 are teenagers, and 0.625 are not teenagers. They're 20 plus. So the total of these two, teenagers and not teenagers, is 1.00, obviously. Good. What is the probability of selecting a participant older than 30? So let's let me get the eraser here, and let's try to, in fact, let me get a colored pen here. Older than 30. No, 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 no. So what percentage of people, or what's the probability of getting someone older than 30? How about 0 out of 8, or 0? Good. So that is answer to 11C. That takes us to question number 15. So in a study on reinforcement, a researcher allows a rat to choose between 4 arms of a plus maze. So a plus maze is something that looks like this. You know what? Let me change this, because we're gonna. Okay, so we're gonna call this a plus maze. So the rat is put right here. So we're going to reward the rat 30% of the time the rat comes in this direction. We're going to reward them. So left, reward 30% of the time. We're going to reward them when they go to the right 30% of the time. When they go to the back, we're going to reward them, but only 20% of the time. When they go to the front, we're going to reward them 20% of the time. So you would not be surprised, right, if after an infinite number of repetitions the mouse figures out, oh, I get a reward here 50% more than I get a reward when I go here. So you would expect the rats to develop a habit of going in this direction. Why? Because total, when they go either left or right, they get rewarded 60% of the time, which is, as a matter of fact, the answer to A. If they go left or right, they get rewarded 60% of the time. So B is this: to make the optimal probability choice, a subject should enter the right or left arm on each trial. And okay, so we answered that question also, because over multiple times you would figure out that you get rewarded when you do this 50% more, it's 30, than when you do either go down or up. Okay, so that is the answer to number 15. The next is number 21, which asks this question. Oh, so here we have some Bayes' theorem here. So this can be tricky, so I want to stick to the logic and not the mathematics. The mathematics is devised to capture the logic. So if you understand the logic, you don't have to worry about the formula and what fits in the formula. So let's do it that way. Okay. The probability that a student passes a class is 0.59. In other words, 59% of students pass the class, which means, of course, 41% fail or do not pass. Okay, so the probability that a student studied for a class is 0.53. Okay, so study equals 0.53. So does not study equals 0.47. Okay, so we have the important probabilities here. The probability that a student passes a class, given that he or she studied for the class. Okay, so the probability, where are we here? I just lost track. Okay, 21, sorry. The probability that a student passes a class, given that he or she studied for the class. So pass over study, that probability equals 0.89. Good. Okay. Now, what is the probability that a student studied for the class? Okay, that a student studied for the class given that he or she passed the class. Okay, so what is the probability given that a student passes a class? Okay, so of the people who pass the class, that's the 59%. What is the probability that a student studied for the class? So, a student studying for the class, we know that pass a class of studying for the class is 0.89, and we know the probability of studying for the class is 0.53. So all we have to do is the math here, and we get, let me figure this out on the calculator, is 0.80. Okay. So this is a probability that a student studied for the class given that they passed the class, right? So given that they passed the class, what's the probability that they studied for the class? 0.53 of these people. So there you have the 0.80, and that's Bayes' theorem. Okay, so that takes us to question number 31. That last one sounded a little complicated, so give it a whirl a couple times and check the text for a more extended explanation of that. Okay, so 31 is probability of first marriage among women. So this raises an important issue, not in terms of marriage among women, but a little bit of a statistical issue. Okay, so let me preface that by saying this. Let's say the odds of you winning a race are 1 out of 4. And you have a sibling, a brother. And the odds of your brother winning another race are also 1 out of 4. So what are the chances that both you and your brother will win a race? So how do you figure that out, right? So here's you win, here's you lose, you lose, you lose. So in this case, you win and your brother has the same odds, so your brother would lose, 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 and win. And in this case, your brother would lose, 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 and win. And the same with these others, right? So in this case here, this case right here, both you and your brother would win. So when you win, there are 4 chances in terms of your brother. When you lose, each time you lose, there are 4 chances of your brother. So your brother would win here. Your brother also would win 1 time here and lose 3 times. And your brother would lose 3 times here and win 1 time there. So the chances, how many total chances are there? There's 4 here, 4 here, 4 here, and 4 here. So there are 16 chances. What's the probability that both you and your brother will win? It's only 1 time out of those 16 chances. So how do you get that? You get 1/4, a quarter times a quarter equals 1/16. Okay, so the question here is, given these probabilities that 6% of women in the United States married for the first time by their 18th birthday, what are the chances that the first and second daughter will be married at 18? Well, the one will be 6%, the other is 6%. So just like we did up here, you multiply them and you get 0.0036. So you get 0.0036. Okay. Now the next one is if the chances of the one person getting married by their 25th birthday is half, or 0.50, and the chance of the other person get married by their 25th birthday is half, that would equal 1/4, right? Or 0.25. If you want to do it this way, equals 0.25. Same thing. So then the question is, what is the probability that they both will be married by age 30? So you see the probability of that is 74% for each. So you multiply these two things and you have, let me do the math here, 0.5476. So you could see that, right? If the likelihood of one getting married by age 30 is 74, the likelihood of both getting married is no higher than 0.74, because the second person will get married by that time only 0.74, 74 hundredths of the time. Okay. Now, that's the math of this question. What is missing here? What is missing here is that in probabilities, you can't multiply these things unless these are independent factors. That means the one has nothing to do with the other. You running in the race, your chances are 1 out of 4. Your brother running in a race and winning it, his chances are 1 in 4. Okay, let's say both of your chances are 1 in 4, but let's say if you get plenty of rest and you have a healthy breakfast, it's higher, and when you don't, it's a little lower. Well, since your brother lives with you, chances are, if the house is quiet at night, you both will get plenty of sleep. Chances are, if one of your parents decides to make you a healthy breakfast early in the morning, way before the run, something easily digestible, some carbs, pancakes, then you'll have it, your brother will have it. In other words, what I'm saying here is that those probabilities are really not independent in this case, unless you and your brother live in different places. But they are more dependent if you and your brother are sharing the same lifestyle, and guess what? If you and your brother are sharing the same DNA. So, okay, I may have overcomplicated that, but remember, this course is about problem solving and not just mathematics, so you should be able to think of things like that. And that was the answer to 31. And you could see, right? So if the likelihood of someone getting married, of a woman getting married is 6%, getting married by their 18th birthday, well, I mean, there are some families, I mean, not some families, but if someone gets married young, it's likely that people raised in that family get married young based on the pressure of their parents or the non-pressure of their parents. So in that case, these percentages would not be completely independent. That was a 31, and that leads us to 35. So presenting bets as a probability or relative frequency. So Tunney in 2006 was interested in various probability relationships. Specifically, he was interested in how the presentation of probabilities influences participant choices. The following is an example of how he presented bets for frequency and probability. Both statements say the same thing for each bet, but in different ways. So there's probability and frequency here. Okay, so don't get flummoxed by this. Let's take the p-bet. The p-bet has a 95% probability of winning 350 plus, so let's do this, right? Or this. Plus, it has a 0.05 probability of losing, so minus $1 or whatever that currency is. I guess that's a lira, I guess. So alright, so all you do is, what's the value of the p-bet? The p-bet's value is 0.95 of 350, right? So gee whiz, so 3 times, hang on a second, I have to get to a calculator here. Okay, so if you do the math here, you'll come up with a p-bet value of 3.28 pounds. That's the value of the p-bet. Okay, what's the value of the other bet? So the pound bet. Oh, I see what they're doing. Okay, so this value is expected to win 40% of the time. It's expected to win 11, and 60% of the time, which is what you have left, right? 60% of the time, it's expected to lose minus 250. So again, you just do the math here, right? So you have what's 40% of 11 is 440. The math here is a little easier. So we have 2, that's 120, so that's 150, so that's minus 150. So what does this equal? Plus or minus is minus, so you have 440 minus 150, and that equals 290. So the question here is, where would you bet? If you're going to be doing some long-term betting, I have much better odds here than I have here. So this is the preferred bet. And I guess that's the question, right? Based on this table, A, what is the mathematical expectation for winning the p-bet? This is it. And what is the mathematical expectation for winning the pound bet? This is it. Based on the mathematical expectation of making p-bets and pound bets, if you had to make one bet, which would you make? And the answer is this guy up here. And explain, I think we just did it. Okay, so those are the answers to Chapter 5. So let me say this, I'll create a second video for Assignment 3, and I'll call it Text 3. Assignment, Stats Assignment Text 3. 3A, 3B. So this will be 3A, and I'll make another one and I'll call it 3B. So I'll talk to you in a sec.